Hi everyone, and welcome to the third and final video for Unit 4, Plane Motion. In this video, we're going to take a look at a second method for calculating velocities in plane motion. This method is called the Instantaneous Center of Rotation, or Instantaneous Centers. The Instantaneous Center of Rotation has zero velocity. And as I said at the end of last video, the special case of a wheel is a good segue into this video, and that's because we have an example of an instantaneous center. Since by definition this instantaneous center of rotation has zero velocity, then that would be the point of contact of the wheel to the ground. As we had shown numerically, that point has a velocity of 0. And we're then able to calculate velocities at any other point on the wheel by drawing out the radius arm from that point to any other point. Now, one important thing to note here, as we see as the last point on this slide, is that this only applies to velocity due to the possibility of normal acceleration. So if you're trying to apply this to accelerations, which is outside of the scope of this course anyways, but if you are, remember that instantaneous centers only apply for velocities because of the normal acceleration when dealing with accelerations. So let's look at an example that we used in part 1 of this unit. And that is a link that's resting up against a wall. So I'll just draw this out. Okay, so here's the link that's resting up against a wall, and at this instant we see that the point at A has a velocity going down, which is following along the wall, and at point B it's going to the right, which is following along the ground. So one important point about instantaneous centers, we'll just go up to the first slide here, is that this is a point about which all velocities appear as tangential velocities. And so that means that if we were to draw out lines that are tangent to the known velocities, so in this case that's velocity A and velocity B, we should be able to find this instantaneous center. So I'm going to start with point A, and I'm going to draw out a horizontal line just because the velocity itself is vertical. So that would be normal to the velocity itself, and then I'll do the same for point B. And I do it above point B mainly because I know that this instantaneous center has to coexist with all other points on this link. And so we need to find the intersection between these two points. And that intersection is our instantaneous center. So what we're saying is that at this point, it appears that all other points are rotating about this point at that instant. So now the great thing is that we can then draw a radius arm from point O, from that instantaneous center, to any point on the body. So we're going to do that, for example, to point C here. So I'm going to draw this radius arm. Okay, and now what we're going to say is that the velocity at C has to be 90 degrees to that. So I would draw out a radius. So I drew out my radius arm. Now the velocity at point C is 90 degrees to that radius arm. So this would be velocity C. And I could do the same for any point on that body. So some more notes about instantaneous center is that a velocity vector of a point relative to the instantaneous center is always at a right angle. And that's what I just showed here, is that we found the instantaneous center by doing right angles from point A and point B. Once we have that location, then we can find the velocity, the direction of any other velocity on that body. The instantaneous center of rotation can only be used on points that are on the same object or member. So this is really important. If you have a number of linkages, so this is just a simple single linkage, so this works. If we had multiple linkages that are tied together, you would have multiple instantaneous centers. You'd have to find the instantaneous center for each individual body. And lastly, the instantaneous centers applies at, of course, the instant only. It's easy in some cases to think, okay, well, it's at this point at time A, it's at this point in time B. Yes, but as soon as anything moves, that instantaneous center moves along with it. This is why it's called the instantaneous center of rotation. It's only for that particular instant. So let's look at an example to put all of this into practice. And one thing I'll just say up front, we could take a look at any of the problems that we solved in part 1, and we can solve them with instantaneous centers. So we used the relative velocity method in part 1 of this chapter, in the first video of this chapter. This is just another method for calculating velocities. On an assignment or a test, I will say specifically which one to use. There are certain cases where, depending on the information that's given, it's more advantageous to use one method over the other. We're not going to get into that, trying to figure out which one to use. I will just tell you whether to use one or the other in this course. So let's take a look at example 1212, and this is on page 408 of your textbook. I'm going to start by drawing out the example, and then we'll take a look at how we apply instantaneous centers to it. Okay, so in this problem, it asks to determine the velocity at B and the angular velocity omega AB. So we are given that the velocity at point C is 5 meters per second downwards. So based on the motion of link CD being downwards, it is assumed that at this instant, the angular velocity of AB would be clockwise. So I've shown it here. And as I've said before, if you do get the wrong direction, it's not the end of the world, because you'll just end up with a negative value. So remember, we want to start with what's known. We do know the velocity at point C. The first thing we want to find is velocity at B, because it's the next closest unknown compared to, say, the angular velocity AB. So we're going to try to solve for the velocity at B. Now remember that instantaneous centers only work for one body at a time. We don't really need to worry about the body or link CD because we already have a velocity at C. So really what we're going to do is just look at link CB. And that's because we're given at one end, we're given a velocity. At the other end is the velocity that we need to find. So in order to isolate this, let's take a look at just that link on its own. So I'm going to go ahead now and I'm going to draw the link BC. And we do know that, again, that velocity at C is downwards. So this is VC. Now, one of the things that we do also know that's not shown on here is the direction of the velocity at B. You might say, well, how is that? We can't tell by this link on its own. By just looking at link BC, we wouldn't know the direction of velocity B. However, it is directly connected to link AB. And since AB is tied to point A, we know that the velocity at B must be 90 degrees to that arm. So if I draw that on our original figure, it would look like this. So this is VB, and it's 90 degrees to the original arm. So if I draw it on this new figure, it looks something like this. So it won't be 90 degrees to to arm BC, but it is 90 degrees to AB. So this is where it's going to get a little tricky because we're going to need to figure out the geometry from here. Before we do that, though, we can find the instantaneous center because we have two known directions on this link. So all we have to do then is draw lines 90 degrees to the velocities that are given, and we find the point of intersection. So we can do that. We'll start with velocity at c. So I'm going to draw a line straight out like this. And then I'm going to draw a line 90 degrees to VB. So we can see that it's going to be sort of out, maybe out here somewhere, because I'm going to draw this line. Kind of missed it a little bit here. It's okay. It's good. Close enough. So there and there. So that is our instantaneous center right there. Point O is our instantaneous center because we've drawn two lines perpendicular to the velocities that are known, and the point of intersection is that instantaneous center. And so one thing we do know in addition to this would be the angular velocity about point O, right? Because that would be the angular velocity of BC. So we don't know what that is yet, but we do know that it occurs about point O. Then how do we calculate the velocity at B? Well, remember VB is equal to R omega. Which R and which omega? Well, it would be the radius arm from B to the instantaneous center. So this would be R OB, and it would be omega BC. So I'm just going to move that omega BC here out of the way so you can see that I'm talking about this radius arm right here, ROB. So I would need to know the distance from O to the distance B, and we also have the angular velocity BC. So if we can find those two, then we would be able to calculate the velocity at B. So how do we get to, I would say first, the angular velocity AB? Well, we have to start with what's known. The other known that we have here is our velocity C, right? So velocity C would be equivalent to our OC times omega BC. If we rearranged, we could solve for omega BC, which would be VCR over ROC. So now we just need to find ROC, which is this radius here. Okay, so this is what I was talking about where it maybe gets a little tricky because we now need to figure out this geometry, which is not directly given. And if you're trying to follow along with the textbook, they come up with a value here almost out of thin air, really. So I want to work through that with you. How do we determine what these two radius values are? So how we do this is we're going to have to take a look at all of the geometry that's given to us over here. We have horizontal and we have vertical distances between linkages. So we're going to have to use that to our advantage. So for this particular problem, what I'm going to do, I'm just going to go over here and I'm going to redraw this so we can see what we have here. I'm going to start with link AB. If we look at AB, it looks something like this. We've got A, we've got B. And what we do know is that the vertical distance here is 1 meter. We know the horizontal distance is going to be, well, let's go all the way back here. We can see that it would be 1 meter plus 0.3 meters. So this is 1.3 meters. AB is equal to the square root of 1.3 squared plus 1.0 squared. So AB is equal to 1.64. That's 1.64 meters, shown right here. Okay, so that is just for the first link. Now, if we look at the second link over here, what has happened with that distance ROB? That actually follows link AB. And transcribe that over onto our original figure. What we're going to see is that this extends out, right, until it hits the horizontal line. And so what we end up here is a much larger right angle triangle compared to the first. But interestingly, compared to what we have here, it is just an extension. So all this is I'm extending this out further. And so my question to you then, what does that make these two triangles? If they all have the same angle, they share this top angle up here, they both have right angle triangles, and so that means their other angle, we'll call beta, then has to be the same. If they have all the same angles, that means these are similar triangles, which also means then that the distances are just ratios. So if we know that the bottom distance of the smaller triangle is 1.3 meters, then we should be easily be able to calculate the distance of the bottom triangle, which in turn would help us solve, if we follow this here, solve for ROC, because we already have this distance right here. So if we know what the total length is, then we just need to subtract the two, right? So what is the ratio? Well, we do know, in addition to this, we also know that this is 1 meter and this is 1 meter. And so the total distance is 2 meters. So that ratio is just 2 to 1. That means then that this total distance here is 2.6 meters, just 2 times 1.3 meters. Therefore, ROC is equal to 2.6 meters minus what? If we go all the way back, it would be minus that 1.3 meters right in here. Okay, so let's do that. Minus 0.3 meters. So ROC is equal to 2.3 meters. So that's quite a bit to kind of take in. I'm going back and forth between some figures here. I would suggest, if that was really confusing, to pause the video, kind of go back and make sure you understand that. The thing here is that we've got like triangles or similar triangles. So I'm using the original geometry to then calculate the geometry of the larger triangle. And that larger triangle tells us distances for that second link here. So we do have ROC. Since we have ROC, that means we can come here and calculate omega BC, which is equal to 5 meters per second over 2.3 meters. So that gives us an omega of BC equal to 2.17 rads per second. Great. Now that we have that, we can take this value and plug it into this equation now, right? We're still missing one more value there, and that would be what? That would be our ROB, right? ROB. But we do have the horizontal and vertical distance of this triangle, right? We just calculate. We know that the vertical distance of this larger triangle is 2 meters, whereas the horizontal distance is 2.6 meters. And so we can then calculate, from that, we can calculate the total distance. So that means that where ROB is equal to the square root of 2 squared plus 2.6 squared. So ROB is equal to 3.28 meters. So we sub that in, we have 3.28 meters times 2.17 rads per second. So VB is equal to 7.13 meters per second. Now the question is, at what angle? Normally I always say, let's try to find this relative to the horizontal. So if I'm going to draw out a horizontal line from VB, I'm talking about this angle right here. And this angle would be, we'll use a theta again, and I'm going to say it's a total 180 on this side. So 180 minus, we do know it's minus 90 because that's this angle right here. So all we're left with is this other smaller angle in there. Well, that smaller angle is the same angle in the corner here, right? Right in that corner, it's the same angle. So we would have to calculate that angle, which you can easily find since this is a right angle triangle. I'll let you do that. You should be able to find that that is 37.6 degrees. And so theta is a total of 52.4 degrees. So if I go back here, that means that VB is 7.13 meters per second at an angle down like this of 52.4 degrees. And that's our final answer for VB. So let's finish off this problem. We have omega AB defined. Okay, now that we have velocity at B, omega AB should be pretty straightforward, right? So I'm going to go down to the end here and I'm going to say that VB, again, just using the same equation, that conversion between linear and angular velocities, it would have to be RAB times omega AB. And that's what we're trying to solve for, omega AB, right? So omega AB is equal to VB over RAB. Well, RAB is just 1.64 meters. That's what we found, right? That's what we found right here. And so we take our velocity at B that we calculated to be right over here, 7.13. So that's 7.13 meters per second over 1.64 meters. And so omega AB then is equal to 4.35 rads per second. And that's the answer for the second part of this problem.